So hello everybody and welcome to today's webinar. Welcome and thank you so much for joining us from all around the world. My name is Uni Kassel. I'm the Deputy Executive Secretary at the International Solar Energy Society, and I'll take you through the first 5 minutes and give you a short welcome and introduction about the International Solar Energy Society. So you're all very welcome to today's webinar, which is a webinar of the IEA Solar Heating and Cooling Programme Solar Academy. The title is Price Reduction of Solar Thermal Systems. We're looking forward to all of your participation and also, of course, your questions in our Q&A session later. Before we begin with the webinar presentations, I would like to inform you a little bit about what ISES is and what it stands for. So the International Solar Energy Society is a non-profit UN-accredited membership NGO. The ISES vision is to achieve 100% renewable energy for all, used efficiently and wisely. We represent a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ISES works together with like-minded organizations from countries around the world to really advance the renewable energy transformation. So please check out our websites. We have two websites, www.ises.org, that's the home page, and join.ises.org. That's where you can find out all about our memberships and you can fill out the online membership application. As explained, ISES is a non-profit organization, and therefore we really do rely on not only memberships but also on donations and sponsorships. If you like the work that we do with these webinars, our conferences and our outreach, please consider making a donation. Even a small amount goes a long way to support the work that we do. If you are already a member, just log into your account and you can select the voluntary contribution link. If you're not a member, don't worry, after this webinar, we'll send you a link with some instructions and we hope that you check that out. We will post the recording of this webinar on the ISES website and the ISES YouTube channel, and the IEA SHC Solar Academy will have it also on their website and their YouTube channel, so you can look at it again in your own time afterwards. You are very welcome and encouraged to ask questions at any time throughout this webinar, so we really encourage a live and dynamic discussion during these sessions. To ask a question, select the questions pane on your screen and just type it in. Please specify who your question is directed to. Questions will be addressed after each of the presentations in a Q&A session. We would also like to encourage you to have a look at the ISES discussion forum on LinkedIn to continue the Q&A even after the webinar has ended. Our moderator for today's webinar is Sandrine Seile, Project Manager at the Fraunhofer Institute for Solar Energy Systems. She will give a short introduction to today's webinar topic and also moderate the questions and answers session after all of the presentations. So I don't want to take up too much more time. Without further ado, I hand over to Sandrine and hope you all enjoy today's webinar.
So thank you, Joanna, for this kind introduction. I would also like to take this opportunity to send out a warm welcome on behalf of Task 54 to our webinar on the topic of cost reduction for solar thermal systems. My name is Sandrine Seile. I'm the leader of Subtask D, and I will guide you through the next 1.5 hours. But before we dive into our topic, I would like to give you a short overview of the Solar Heating and Cooling Program of the International Energy Agency. The program was established in 1977, and as you can see on this map, it is a truly worldwide and international research program. It has about 20 member countries in Europe, North America, China, Australia, and South Africa, and additional sponsors from about 47 countries. The SHC is project focused with currently 11 running tasks, and of course also the activities as part of the Solar Academy, such as this one today. Was gone too far. Well, the idea to found an academy arose because we want to share our work and we want to support R&D and the spread of solar heating and cooling technologies worldwide. You can participate in the Solar Academy by different ways. Of course, you can join our webinars, such as the one today. The webinars are held quarterly. But in addition, we also have videos with interviews or presentations of our experts. We organize national days in close conjunction with our task meetings, and we provide on-site trainings. So there's actually a number of outreach activities, and if you wish to know more about these, please visit our website or join us on social media. All of our addresses are summarized on this slide, and I invite you to have a look at these after our webinar is over. Well, our webinar today follows the Task 52 webinar on solar economy and solar heat. And we feel that this is actually a very nice continuation, as this last presentation by Sebastian Herkel and his colleagues also touched upon solar thermal costs and brought up quite a few questions that we feel that we might be able to answer in today's webinar. Why focus on cost reduction? Well, I guess that we all know that solar thermal finds itself in a rather difficult economic situation lately. The installation figures are decreasing and there is rising competition by other alternatives in the heating sector. And all of these have somewhat forced solar thermal into a corner. And this is exactly why Task 54 has been launched 2.5 years ago. With the combined effort of our experts, we tried to really counter this trend and find solutions for cost reduction for solar thermal systems along the entire solar thermal value chain. And today we'd like to share a sample of our results by approaching this topic from a range of different angles. As you can see on our program for today, it's going to be a very dynamic session with a lot of different presentation and a lot of different speakers. We'll try to start this webinar with a short theory part and have an introduction on the solar thermal value chain as we understand it and work with it in Task 54. We will then turn to the calculation method we use for the validation of our cost reductions, and we'll introduce the levelized cost of heat model that we use in Task 54. And these introductory talks will then be followed by 5 practical examples of how costs can be lowered. The examples will cover design aspects, but also materials and application scenarios. And they will also speak about economical means of price reduction or price calculation. And finally, we'll try to bring all of these together in a wrap-up at the end of this webinar. Some of you might notice that the order of these practical examples is somehow different from the ones we announced early on, but don't you worry, they're all in. It's just a different sequence. And of course, as Joanna has also said at the beginning, you're all invited to send us your questions and comments that occurred during the presentations. I will make sure to collect them and we'll answer them all together at the end of all presentations in the Q&A session. And with this, I'd like to hand over to our first speaker, who's Dr. Stefan Fischer from the Research and Testing Center for Thermal Solar Systems at the Institute of Thermodynamics and Thermal Engineering at the University of Stuttgart. Stefan has done his PhD on collector modeling and testing and has over 25 years of experience in national and international projects related to solar thermal and standardization. In Task 54, he leads subtask B, and that is why he will also give us a short introduction on the solar thermal value chain and cost reduction potential.
Thank you, Sandrine. Welcome, everybody. Good afternoon to all of you out there. As said already by Sandrine, I will give a short overview about what we understand under the solar thermal value chain, and also I will give some outlook for the cost reduction potentials. Sandrine, I think I don't have the mouse.
It work? I'm sorry. Does it work now? No, well, in this case, I will
just change,
hand
please.
over the slide for you.
Yeah, thank you.
Mm-hmm.
So first step in the solar thermal value chain is, at least at larger systems, it's an architect, planner, or energy consultant who set up the solar thermal system. Then next, it's a pity now. We have to produce the subcomponents, the components of the solar thermal system. And after the production, the parts of the solar thermal system has to be distributed to the installer, wholesaler, or distributor. After it is distributed, the system will be installed by the installer. And then we will have an installed system, which after it has been installed, we want to operate it. And from time to time, we have to maintain it. So, and at the end, we have the costs of the kilowatt hour solar, which is the levelized cost of heat, which is basically depending on all the steps done before. Now we want to take a little closer look in the single steps. First of all, we have the production. There it starts with the raw materials like copper, aluminum, steel, sand, and oil. Next, we have the semi-finished parts, which are produced from the raw materials like the copper pipe, the aluminum sheet for the absorber, steel sheet for the storage tank, glass, polymeric materials. Out of those, we produce the subcomponents like the absorber, insulation material, glass cover, heat exchangers, or collector frame. And when we put them together, we will get the components like the collector, the storage tank, the controller, and the whole system. Sorry, Sandrine, next. Okay, to do all this, we need, of course, energy, machinery, labor, operation costs, and last but not least, we would like to, or the manufacturer would like to have some profit out of this. Those components are then distributed either by the system supplier or wholesaler. The things are put together to installation manuals and installation kits are added. And to do all those things which are done by the system supplier or the distributor, he needs to add logistics, equipment, R&D, public relations, marketing, and of course, he also wants to have some profit out of this. Then during the installation, again, labor, installation material, logistics, and profits are added to the components and during the installation. And the installed solar thermal system again then needs to be operated and later also to be maintained. And here again we have to put labor, material, and energy into the system. And summing all those steps up will result in the cost of the solar kilowatt hour or the levelized cost of heat. So within this value chain, we have different potentials to reduce the costs. First of all, there's a possibility of materials, use different materials like polymeric materials, but then of course we also need different systems design. Later on, Michaela Meyer will talk about this possibility. Second option is the reduction of the production cost. There, different measures are possible. Process cost analysis, Axel Olivia will talk about this later on, standardization of components, and of course economy of scales, which often goes hand in hand with standardization. Also for the installation process, the process cost analysis can help, but also the reduction of stagnation temperature, because then different materials might be used for the hydraulic loop. Here Bert will talk about later on, and again standardization. Operation can also be supported by standardization due to longer and better operating systems. So this will put down the cost as well. The reduction of maintenance can be achieved by a reduction of the stagnation temperature again, and also with standardization, because the installation is error-free if we have a high degree of standardization. And last but not least, the service time life can be extended, which also leads to a reduction of the levelized cost of heat. And here, the reduction of stagnation temperature as well as the standardization helps. So this was from my side a first introduction to the topic and the value change. And so I would like to thank you at that point for your attention, and I will be back in 10 minutes. Thank you.
Well, thank you, Stefan, for this very good grounding of our session for today. I will now hand over the presentation to my colleague Johan Louvet from the University of Kassel. Johan is a PhD candidate in the University's Institute of Thermal Engineering. And Johan is specialized in solar thermal systems and especially also drain-back systems. And in task 54, he has taken over the lead on the definition and formulation of our levelized cost of heat calculation method. So he's really the expert in this one, and he will explain it in more detail for us now.
Yeah, hello everybody, and thank you, Sandrine, for the introduction. So, as Sandrine just said, I'm going to explain a bit the method that we have developed within the task. And so as you already said, during the task, we want to reduce or assess with which method we can reduce the heat price for solar thermal heat. And for this, we need on the one side to define reference system, which are then a basis to then evaluate how the measure we propose can impact the price of the heat based on this reference system. And for this, we needed a common indicator and methodology in order to do this task. So we've decided to go for the so-called levelized cost of heat. So it's an indicator which is maybe more known in the power sector under the term levelized cost of energy or electricity, but it's also more and more used in the heat sector. We have, for instance, a European project, the FRONT project, which used it and defined it. And based on this, we decided to choose this indicator. And for us, it has the advantage that we can, on the one side, assess the impact of the entire cost reduction along the value chain. So, for instance, about investment costs, about installation costs, about maintenance costs, but it also enables to assess the impact of performance improvement on from our system. Now I will go quickly through a simplified equation. So basically the LCOH is a ratio between cost and energy. And on the cost side, of course, you have the initial investments, which plays a role. And at the denominator, you have a reference energy. So I come back to that after. And so it is a dynamic indicator. So for that, the time series are discounted. And of course, you analyze that over a certain period of analysis, in our case, the lifetime of the system. To the cost, so you might subtract subsidies, possible subsidies that you get for your system, and I lost the mouse, and yes, and you also need to add all the operation and maintenance costs that will occur along the lifetime of the system. So as additional assumption within the task, so first of all, we focus mainly on residential system. And for this, we decided to set the discount rate to 0. So because we consider that the system are usually paid upfront in those cases. And we also didn't consider any subsidies, and we considered all the price without VAT, and that's in order to be able to better compare between different countries. So now, as we all know, solar thermal systems are typical or untypical kind of heating system. You always need a backup system, and for this reason, you can think of different definition of the terms that you use in the equation. Looking at the investment, for instance, should you include the boiler costs? Should you not include the boiler costs? Should you include tank costs? Should you include only part of the tank cost? Looking at the reference energy, which energy should you use here? Should you use the energy which is delivered to the end user, or simply the energy which is delivered by the solar collector field? So basically here you have different options, and that was the role of our group in the task to define what we wanted to do. So here what we did indeed is that we didn't define only one LCOH but 3. And they are all depending on where you set the boundary of your system. So first of all, if you consider the entire solar assisted heating system, then we define the so-called levelized cost of heat for the overall system, LCOHO. If you only consider the solar part here, it was the LCOHS, which is for the energy which is saved thanks to the solar heating system. And finally, as a twin of this LCOHS, we have the LCOHC, which is focusing on the conventional parts of the total system. And this, of course, has an impact on the different terms that we use in the equation. And first of all, I should say that additionally, we need absolutely to define the reference conventional system, which is a system which delivers the same amount of heat to the end customer as our solar thermal system, but without the solar part. And this is necessary in order, first of all, to define to calculate a store credit, which is the cost of the store in this system, which will then be subtracted to the cost of the solar heating loop here. And we also need it in order to assess our reference energy, which is the safe final energy. And if I will look at LCOHC, then the investment cost will be the cost of our reference conventional system, and our reference energy in this case is the final energy consumption of this entire solar assisted system. So now I will go through a short example of this calculation for a reference solar domestic hot water system for a single family house in Germany. So it's a basic solar heating system with standard size, so 5 square meter flat plate collector, 300 liter store with a gas backup boiler. And thanks to simulation, so we calculated the safe final energy and the final energy demand, so the remaining energy demand covered by the boiler amounts to a bit more than 13 megawatt hours. So it's for both domestic hot water and space heating. And we set a system lifetime of 20 years, which is standard for Germany. And looking at the cost now, on the one side, so we have the cost for the conventional system. The investment includes all the cost and the installation costs for the material, for the conventional part, including the storage, so the reference storage. And the operation and maintenance are there for the fuel costs, the electricity cost to run the pumps, as well as the yearly maintenance cost that we get. And on the solar part, so here it's all the costs from the solar loop, including the storage, to which we subtracted, as I just said, the cost of the reference storage. Concerning the operation and maintenance, so here just the cost of running the pumps and the cost of yearly maintenance. So with those figures, now we can calculate the three indicators as I just mentioned before. Here we have the LCOHS, the LCOHC, so here we consider the conventional part. And finally the LCOHO, which is for the overall system. Here we have all the sum of all the cost of all the energy. So in this example I just showed, we see that the solar part has a bit higher cost, and this compared to the conventional part, and this contributes to a slightly increase of the cost of the overall system. So, so this is, as I say, a reference system without any improvement that we considered in the task. So as a short summary, the LCOH is a sensitive indicator, and as I say, we can define different energy, define different costs, and it is very important to always detail the assumption that you use. In the literature, you could find for solar thermal similar indicator, but if the assumptions are not the same, it's then impossible to compare. For solar thermal system, of course, the LCOH depend on many parameters like system design, customer behavior, climatic situation, lifetime and maintenance cost. And this is why it was important. We needed within the task that we detailed. We defined in the details calculation for 10 reference systems for 5 countries, and this can help us, will help us, and can help others to then make comparison with improvement or other system configuration. So I thank you for your attention, and I will hand the microphone back to Stefan.
So thank you, Johan, for this very good introduction to the LCOH method. And now that the basics have been presented, I would like to lead over to our practical examples. And the first one will focus on cost reduction by means of standardization. And for this topic, there's really no one better than Stefan Fischer again. That's why I'm handing over the mouse and microphone to you. And I hope it works this time.
Yeah, thank you, Sandrine. So if we take a look into standardization, unfortunately, it does. In standardization in everyday life, we all know and like standardization. I have some examples brought here. First is the USB. I think all of us know the benefits of this standard, so we can attach any possible device to our computer. The second one I would like to emphasize is the global system for mobile communication, the GSM standard, which makes it possible that we can use our mobile all over the world and can talk basically to everybody all over the world. And another small and nice example is the opener of a beer can. No matter in which country in the world we are, if we have a beverage can, we know how to open it because it's everywhere the same standard. And also the can itself is standardized, and this also leads to cost reductions because the same can be used for a lot of different liquids. So standardization can make life easier and also cheaper. So what are about standards for solar thermal? There, if you take a look at the collector, it's not really standardized so far. We have different sizes and dimensions. Even if the gross area is the same, We have different connections for inlet and outlet and connecting it to the solar loop. There are different locations of the temperature sensors, and there are different interfaces from the collector to the mounting system, which adds difficulties to the installation process. If we look at the mounting system, it's the same thing. There are also different mounting frames, mounting kits, clamps. Everything is not standardized. Yeah, we have different roof hooks, different mounting rails, and different clamps, and all the other stuff which is different. If you look at the hot water storage, there are also different dimensions of the storage tank. Even if the volume is the same, we have different types of connections. The location of the connections are all over the place, so there's no standard at all. And the same is true for basically all the other components. So we are really in a need for standards for solar thermal to improve the systems and also to reduce the costs. Next, please. So what will be the benefit of standards for solar thermal? If we have standardized components, we will have cheaper semi-finished parts, subcomponents, and components, and this will lead to a reduction of the investment costs. If we have another benefit will be a cheaper and mostly error-free installation of the complete system. This will bring reduction of the investment costs as well. But also, and this is a very important issue, is the reduction of the maintenance costs, because if the system was installed error-free, then we usually also have less maintenance costs. And also we will see an extension of the lifetime of the system due to this error-free installation. And last but not least, we have a better performing system because it was easy installed, good installed, and this will increase the saved final energy. So what will be the impact of the standardization on the solar thermal value chain? First of all, if we have standardized components and maybe also standardized system concept, then there's less planning and consultant work needed. During production, it is allowed, or we have the possibility for mass production. This will cut down the costs for the semi-finished parts, subcomponents, and components, and also result in a reduced logistic within the production. During the distribution, we have a reduced effort for packaging, storage, and transportation, because all the components or a lot of the components have the same size or are standardized, so the same packaging can be used by different companies. We have an easier and faster and error-free installation during the installation process. And the installed system will give us a better performance, and more final energy will be saved. And also, it's probably we probably will have a longer service life, service time. During the lifetime, we have a reduced operation and maintenance cost, and last but not least, this will reduce the levelized cost of heat. And how this levelized cost of heat can be reduced or will be reduced if we do a standardization from the beginning to the end, I would like to show with the example Johan presented just the presentation before. So the assumptions that are made here, they are quite realistic. So if we have standardization from all the components, we can have a reduction of the investment costs of up to 10%. And also the investment for the installation can be reduced by 20%. This is basically due to the, or mainly due to the fact that if the installer are used to the standardized components, the installation can be made easier and faster. For the operation and maintenance costs, they can be reduced by 26%, which is basically 30% of the maintenance costs. The operation costs are in this example kept the same. Then if we account for 10% more saved final energy and also an increase of 10% service time, which is just 2 years, we come to the following figures, which I will show in the following slides. In this slide, we have the reference value, which is 100% of the levelized cost of heat. And all parameters are in that way Johan presented just before. And if the investment costs are reduced by 13% due to standardization of the components and the saved costs in installation, we can reduce the levelized cost of heat by 8% in this example. Next is the operation and maintenance costs. Here we can reduce the parameter by 26%. This adds another 10% cost reduction, and the saved energy will increase by 10%, and also the lifetime will increase by 10%. And if we sum all those up, we will find a levelized cost of heat for this typical German domestic hot water systems of 9.8 euro cents per kilowatt hour, which is already a reduction of 30% compared to the reference systems, which was described and introduced by Johan in the presentation before. So I already come to my summary. Standardization is really required for solar thermal. We are far back behind a lot of other technologies, and the standardization leads to easier to install, more reliable and more efficient solar thermal systems. And the cost for the kilowatt hour produced by solar in a standard solar domestic hot water system like we use it in Germany can be reduced by standardization from 13.9 to 9.8 euro cent, and which is a cost reduction of 30%. And the costs in this case are now even 13% lower compared to the conventional domestic hot water system. So this was a very short overview from my point, what standardization can contribute to the cost reduction in solar thermal. Thank you very much.
Thank you, Stefan, for this nice presentation. From what I can see on the comments and question section, standardization was heavily discussed. There are also quite interesting questions coming up. I hope we'll have time for them in the end. There was also the worry that we are going to talk about standardization too much and not talk about innovation. I think I can calm those people who were worried about this, because we're actually also going to talk about innovation on the technological and the economical level. And I think we're starting with some economical ways of how to reduce costs. This question is actually tackled in a project called TEWIsol, and I'm very happy to introduce my colleague from Fraunhofer ISE and also project leader of TEWIsol, Axel Oliver. Axel has joined Fraunhofer ISE in 2009, and since then he has worked with solar thermal systems with a special focus on component design, hydraulics, or control strategies for solar thermal heating systems, and much more actually. But in TEWIsol, he's working on process cost analysis for solar thermal systems. So this is a rather economic topic, and I'm very much looking forward to hearing more about it. So
Hello from my side. Thank you very much for this introduction. I will present some issues we perform at Fraunhofer ISE related to this task. And I would like to start with my first slide, where the targets that we do are written down. First is that our project activities are common activities with industry, craft, and also research partners, targeting cost reduction in solar thermal installations. So the actors that are included in our work are, on one hand side, manufacturers of solar thermal systems, but also component suppliers and installers, and finally, research institutes. The approach in our work is to combine economic technical methods for the development of cost reductions in the industry, considering the complete value chain, starting from development until installation on the customer side. So in this slide, I would like to introduce three main parts of methods that we use for cost optimization on the side of economics. First, there is a complexity analysis to be mentioned. Complexity analysis means that by that, the diversity is determined that is needed by the market expectations of a company's portfolio. So this is more or less an external complexity that is shown to the customers, to the market expectation by the portfolio of the company and its product range. On the other hand side, we look in the complexity analysis at complexity of the existing product structure of the company. That is called internal complexity, and means what complexity, what variations of products a company has to realize to serve the market expectations. So market expectations look in a different way on products than the company actually does by itself and its variants that it is setting up. So reduction of complexity and management of this diversity is one main part of the project. Second, process chain analysis is being performed, and by that indirect cost drivers are being identified. That means that cost effects based on product complexity are being quantified and put to a value that we call indirect cost. So by this measure, a modeling is being performed to get an indirect cost factor for our product. And third, a value analysis is being performed where basically the function of a product is being analyzed regarding to its components, so that the direct product-related cost will be analyzed, and direct cost and indirect cost will mean the total cost of the product finally. So on the next slide, I would like to introduce the methods that we perform on the optimization level on the energy part. First, there is the identification of the solar yield of the system that depends on its components and the design of the entire system. This is done by the benchmarking of systems and measuring components. Second, in this part, we do simulation-based analysis to get results for the components and the systems we look at to get a performance optimized output of the system regarding to different factors of the system design. With this slide, I would like to introduce on the x-axis the standard, or let's say the portfolio of one company and its product range. And on the y-axis is shown the quantity and pricing and cost that I would like to introduce later. The graph will tell you how the product range of the company historically used to be. There's one standard product with a high quantity and little variety being sold in the market. So the company used to be in history quite specialized. Today, the situation has changed. The market expects a high range of products, a high variety to meet customer needs. So the standard product is not really the selling part anymore, and the company is driving more and more towards exotic products to meet customer needs. So now we can see with this red curve the real cost allocation for those products. And as you can see, exotic products are quite expensive, while the standard products are quite cheap for the company, for the view of the company. Once you apply for this product range an undifferentiated pricing, you can see that there are differences regarding to the real cost allocation that we would like to get in the project work. And you can realize that exotic products lead to a loss of cost. So it's not economically to sell this, but it's a good reason to have these products in your range, in your portfolio. And you can see that the standard products, you get a competitive disadvantage regarding to other companies because the product is placed in the market too expensive, and that this will lead to even a higher variety of products and more exotic products that actually finally will destroy and make the entire company not economically work anymore. So what we are about to do is within our work to put these cost efficiency factors together by modeling direct and indirect cost by cost analysis, and to combine it with the energy efficiency of the systems that was already shown by the levelized cost of heat that include both terms, cost and thermal and energy efficiency. And by optimization of both parts in one tool, we get a finally highly optimized product for the market. So what we've done is by our work is a new integrated method for a combined techno-economic optimization of solar thermal systems that include the complete value chain of the product from its development to the installation and the end consumer. The approval by this method is being performed by including industrial partners on one hand side and also craft partners in the project. So finally, the identification of a first optimization potential for these project-related individual partners is being performed, and is by that possible and valid for the entire solar thermal sector. So I would like to thank you for your attention, and I'm looking forward for any questions you have. Thank you very much.
Thank you, Axel, for this very interesting presentation. We've now heard how cost reduction can be achieved by design aspects or by economical means, and we'll now move on to another innovation in design, which is going to be presented by Bert Schiebler. Bert Schiebler has studied renewable energy systems and has joined the Institute for Solar Energy Research in Hameln in 2013. He's part of the R&D department of solar thermal collectors and leader of the project Cost-Efficient and Reliable Solar Systems with Novel Heat Pipe Collectors. And he will now share some of his results of this project. Bert, we're looking forward to your presentation, and I'm handing over the mouse to you.
Yeah, thank you for your for the introduction, and good afternoon from my side. I would like to speak about the possibilities of avoiding stagnation loads by collectors with temperature limitation. The focus is on the levelized cost of heat calculation of solar systems with such collectors. Yeah. The next slide doesn't work. Yeah, yes. There are different approaches for temperature limitation, for example, by cooling drain bag systems or by the simple shading, but additional components are needed for that. Other technologies are based on switching technology, which let increase the heat losses of the collector at high temperature levels. For example, by thermochromic absorber coatings, by thermomechanical valves, or also by heat pipes. We focused on inherently safe systems. That means that the collector power is automatically shut off at a certain temperature level. You can see it in a geometrical drawing of exemplary collector efficiency curve. In stagnation mode, the maximum fluid temperature is significantly reduced, and vaporization of the solar fluid can be avoided. In consequence of this, the solar system design can be simplified and the lifetime of several components can be extended. To reach temperature limitation like this, we have different R&D activities in the IEA task 54, which distinguished in the shut-off technology. In the case of heat pipes, physical effects inside the heat pipe limit the heat transfer ability between the absorber blade and the solar circuit at high temperatures. In the case of thermochromic absorber coatings, the emissivity as an important optical parameter of the collector is shifted from 5 to 40% at a high temperature level. So the heat loss coefficient of the collector is increased and the stagnation temperature is reduced. Another approach is given by the SPF, the Institute für Solartechnik, by the University of Applied Science in Rapperswil. And the approach is based on the shifting of the absorber to the front glazing. That means the distance between the absorber and the glass is minimized at a high temperature level. And also the heat losses are increased for that, and the stagnation temperature is reduced. By such temperature limitation, next slide. Yes, by such a temperature limitation, several simplification in the solar system design can be realized. For example, by polymeric pipes. And polymeric pipes can be used for a wide range of the solar piping, or the expansion vessels can be made smaller, and also the solar station can be optimized. We sum up the benefits on this table, and we divided the calculation in two parts. The general system, which represents an unspecific approach for temperature limitation, and the heat pipe system, which is a more concrete calculation and considers further properties given by the concrete technology. For example, that less solar fluid is needed in the case of heat pipes. As reference, we consider the task 54 solar domestic hot water system as presented by Johan today. Please note, it's quite difficult to determine these costs with a high accuracy. So we defined ranges of the benefits which are determined in agreement with practical partners. In the case of the expansion vessels, we get a benefit between 100 and 140 euros. The cost reduction by polymeric pipes depend on their possible amount and is up to 200 euros if 100% can be replaced by the polymeric pipes. In the case of the solar station, we come to a benefit of 20 euros until now, but we assume that the completely new version based on cheap polymeric materials can reach a benefit of up to 100 euros. Another important point is the reduction of the maintenance costs, because thermal and mechanical stress is avoided, so that the lifetime of components and the general service intervals can be extended. We determined the individual maintenance effort for each group of components. And we have seen that the focus is on the solar fluid, which is the most important cost driver. By avoiding stagnation loads, the lifetime can be extended to 10 years. And in the case of heat pipes, we consider, in addition, an easier changing procedure, and that less fluid is needed. In the graph, you can see the whole maintenance costs for each system and the individual cost drivers. Our estimated costs ranges between 42 and 52 euros per year in case of the general system, and 34 to 46 euros per year in the case of the heat pipe system. That's a reduction by more than 50% compared to the maintenance costs of the reference system. You can see that the most important benefit is forced by the solar fluid. The average maintenance share of the levelized cost of heat is reduced from 32% in reference system to 18% in general and 16% in the heat pipe system. Now we come to the levelized cost of heat. There are the solar investment and the maintenance effort, which are reduced by the mentioned benefits, and we have the annual yield. Also for the annual yield, we assume that the general system and the heat pipe system reach the same performance as the reference system, despite the point that the expected annual yield of the heat pipe system would be slightly higher as consequence of, for example, better heat loss coefficients. We set it equal to have the focus only on the benefits by temperature limitation, not by a better collector insulation or something like else. The levelized cost of heat for the solar part ranges between 9.0 and 11.1 cents per kilowatt hour, and is slightly higher and lower for the heat pipe system. Compared to the about 14 cents of the reference system, it's a reduction of up to 34% in the best case scenario. Here you can see the chart with the levelized cost of heat for each system and the individual cost drivers, an example by the components, by operation, or by installation. And it's seen that the most important effect of the cost reduction is forced by the maintenance costs. Lastly, I have to note that we will hold on all these informations about the possible cost reductions by temperature limitation in 2 info sheets. I will prepare it as soon as possible, and you have the chance to download them on the Task 54 website next time. Thank you for your attention, and I have to pass on to Michaela now.
So thank you, Bert, for this presentation. I will now hand over to our expert in material substitution, which is Dr. Michaela Meyer. Michaela is a physicist and also an R&D leader of the Norwegian company Aventa AS. Aventa is pioneering in the manufacturing and installation of polymeric collectors, and how costs can be lowered by help of new materials will be the focus of her example. Michaela, I'm passing on the mic to you. Michaela, are you here?
Thank you. I'm online. Thank you, Sandrine, and welcome to the part of our webinar which deals with the cost reduction potential of polymeric collectors. So, what are the Yes, thank you. What are the main characteristics of polymeric collector systems compared to systems with conventional flat plate collectors of metal and glass? You see here an example of a conventional system of conventional collector to the right-hand side. The core of a collector where polymers are used consists of the glazing and the absorber. In particular, for the absorber, there is a high temperature performance polymer used. The advantage is of using polymeric materials that it can be, in this case, provided in flexible lengths. The design provides lightweight modules. Here we have the text, I apologize. And we are replacing with this technology conventional building envelopes, and both for roof and facade integration. If we look at the system side, the heat carrier is pure water instead of glycol mixture with water. These are high flow systems for optimal cooling of the polymeric absorber. It's drainback technology, and it's non-pressurized collector loop, which means that several safety items, which are in the overall installation are not needed. So if we look at the major production steps, oh, I'm sorry. Here we are. Let's have a look at the production of polymeric collectors. To our opinion, the number of production steps is significantly reduced compared to conventional solar collector production. If we are looking here on the pictures shown on the slides, which are in a way the major steps, there we have in a way the online production for the absorber, which is done by extrusion, both for the absorber actually and the glazing. It is cutting these into the right length, assembly of end cups on both sides, cutting of other subcomponents, shipping, and transport and installation. Presently, the largest increase in value happens in the absorber production. If you look at the image to the right-hand side, you see the absorber, which consists of a top and bottom end cup, both injection molded parts, and the absorber as an extruded sheet. These are connected by infrared welding, a highly automated welding process. And the processing in polymer production are in a way giving a high potential for cost reduction, especially if volumes are increased. It's very few production steps, and it's also integrated design possible. For example, looking at the bottom end cup, where you have already the manifold included in the design. And what we learned earlier from the presentation of Stefan Fischer, that standardization is very important. And here it's actually PEX piping, as you know it from floor heating, which are used together with the connectors. So this is in a way parts known to installers. I mentioned the considerable weight reduction when polymeric materials are used. Here to the left-hand side, I use the example from Stefan Fischer, which is a study of solar combi systems from 2008 with conventional flat plate collectors, and compare this on the right-hand side with a concrete example, in fact, that's what you see here on the pictures of combi systems with polymeric collectors. And you see here the share of the different materials in both figures. main part is stainless steel, related to the heat store in first of all. You see here on the left-hand side, glass, copper, and aluminium contributing to the collector. And on the right-hand side, the polymeric materials, which make in a way the largest part of the Aventa-based technology. The aluminium is mainly connected to the framing. If you add up all these numbers, which are given in kilograms, you end up on the right-hand side with approximately 530 kilograms. And on the left-hand side with 530 kilograms, and on the right-hand side with approximately 230 kilograms. So this is more than less of 50% of the weight. Of course, if this comparison is fair, it can't be said because I don't know exactly which example is used to the left-hand side, but it gives at least an indication that the weight is considerably reduced. When we look at the solar thermal value chain, there are 3 central issues which we mean contribute to simplifying the process and lead to cost reductions. One issue is under point 3, where there is no wholesaler involved in the case of this polymeric collector concept I'm describing. So it is in a way delivered to the building site directly from the producer, and which means this is sales business to business. The second part is related to point 4, that the installation, that the solar products are lightweight, easy to handle at the building site, and no specific infrastructure or cranes, except for those which are already on the building site, are needed for the collector installation. So the collector is in a way the collector installation is a part of the whole building process. It's also actually so that the collector is standard width, which fits to the standard building width in Norway. So it's both 60 centimeter, which is in a way straightforward. Point 3 is due to the non-pressurized design, it's also easy that in the installation process that not the authorized heating installer is required, but it can be done by any other skilled installer like a carpenter or roof installer. I don't show any qualitative figures here, but I will come back to this on my last slide. I proceed here with, when it comes to smaller systems, I show here prices of solar heating system in private homes. This is a study from 2015 performed by the engineering company Asplan Viak together with the Norwegian Energy Society. It reports the total end user costs, including solar collector system, heat store, including installation, but excluding VAT and subsidies. And what we can see here, that is we have three categories, 3 lines. One connects to flat plate collectors of conventional technology, one to flat plate collectors of non-pressurized technology, which is the polymeric concept, and one to vacuum pipe collectors. And you see clearly that for this type of systems, that smaller size system, that the best costs are reported for, the lowest costs are reported for the non-pressurized technology. On my next 3 slides, I will present cost examples of 3 different projects, which I will compare on my very last slide. The first example is a medium-sized project. It's Ilseng State Prison in Norway with polymeric collectors, 237 square meters. It's 8.4 cubic meter heat store. In the technical room, it's a retrofit project. The costs I'm giving here is related to collectors, heat store, pumps, control system, pipes, removal of existing tiles, as it was a retrofit project, and installation, engineering, and administration. And we end here with a collector, also with a cost of 433 euros per square meter. If you normalize it to the collector costs. Collector area, I apologize. I do the same for my next example. This is Björkelangen Elementary School. It's a new build project. Here you see the collector on the facade, on roof part of the roof here on the facade of this installation. It's a solar heating system for domestic hot water preparation. It's 105 square meter facade integrated collectors and 5.6 cubic meter heat store. Yeah, but if you look at the price here, we have 370 euros per collector area, per square meter collector area. And this price does not include, in a way, the savings of the materials which elsewise have to be placed on this facade. And my last example is housing estate in Oslo with 34 passive houses. Here we have totally 840 square meters divided on these 34 different units. It's decentralized heat storage with 0.8 cubic meters heat store. It includes also, the costs include also 100 liters domestic hot water preheater, piping, operation control, auxiliary heat supply, and solar heating system installation and startup support. And here we also end up actually with 370 euros per square meter collector area in costs. So, and I try to make a comparison on my last slide. Here I try to use our LCOH, so the life cycle cost of heat tool, to compare these three systems of my previous slides, as you see them here. I give here also the irradiation on the solar irradiation, not on a horizontal plane, but on the collector plane in order to express deviations from south or the azimuth angle or a tilt angle, which is reducing the solar irradiation on this collector surface. So if we look here what I calculated, and yeah, what we should in a way consider as well is in the picture to the left, to the right top, you see what I calculated here. It is the only the solar part of the complete solar heating system. So I'm only looking on the LCOHS part. The auxiliary part is not included in that case. And we have, for the example to the left, Ilseng State Prison, we have 0.099 euros per kilowatt hour in levelized cost of heat. This is compared to 0.035 euros per kilowatt hours for the elementary school and 0.082 euros per kilowatt hour for the passive house estate housing. Reasons for these differences. I have indicated some in my last row. The left-hand side, of course, much of the costs went to a removal of the roof tiles, that it was a retrofit project. The project is not optimally oriented to the south. It has therefore a lower performance. I calculated also what would the costs be if it was a new build project, and then we end with somewhat better life cycle costs of heat, which is 0.073. If we go to the elementary school, the reason that we have here so low costs, this is that it was good planned. It was easy to access, to install it on this on the roof here, as you see. The infrastructure between collector system and heat store were short. It was no long piping required. So, and another thing is that it's not a disadvantage to have it in a way facade integrated, because the school has in a very low lower demand during the summertime when the sun is high. So this is in a way fitting in a way well with the facet integration and the usage as domestic hot water system. The housing estate here, the costs here are somewhat higher. And of course, because you have decentralized heat storage, you have small system and each of them needs their infrastructure. But it was also required to get a very high solar fraction. So the systems are slightly overdimensioned in order to, in a way, access some subsidies. So we had to have a solar fraction of 60% here to get when the system was planned. You see that I haven't done this in a very classic way as described by my colleagues before, that I have defined a reference system, and also the auxiliary part hasn't been compared in the whole picture. But if you compare here to the electricity costs in Norway, then you can see that this is in a way systems which the additional part which you have to in a way invest for the solar heating installation, which is giving a quite competitive figures. Okay, thank you for your attention. I would like to hand over to the next speaker.
Thank you, Michaela, for this presentation. I thought that the listeners found it very interesting, and there are bound to be some questions to answer afterwards. We're slightly over time, but I hope that this doesn't refrain us from looking forward to François' presentation. I would like to introduce Dr. François Vainant, who is a process engineer and doctor in renewable energy from France. He works at IEA, Institute for Sustainable Technologies in Austria, since 2016, and his research focuses on concentrating as well as non-concentrating solar thermal technologies and hybrid energy systems with applications for buildings, small productive use, and industry. And today, he will give us an overview of system costs for multifamily houses and maybe hold some surprises for us. François, I'm going to hand over the mouse to you.
Yes, thank you, Sandrine. So about cost competitiveness of multifamily house systems. I will talk about the levelized cost of heat for multifamily house systems, then show some examples of the way to ensure low costs, and also explore some further cost reduction potential. About the levelized costs of heat in multifamily house systems, the reference systems have been defined within the task 54, like Johan presented, and typical hydraulic circuit has been used for simulation, and the levelized cost of heat so is derived from the investments, the running cost, and the energy yield over the lifetime of the installation. And if we look at this table, we can compare some systems. We can compare between multifamily house systems, single-family house, as well as see the levelized cost of solar heat in comparison to the conventional heat, and this in different countries. The first observation is that there is a significant variation in costs between the countries, which can be due to the solar resource or technical practices, as well as legal framework. We see, for example, in Switzerland and Denmark, the specific investment is much higher than in other countries, but the yearly maintenance cost is also significantly lower, and the lifetime longer, which leads to comparable levelized cost of heat. Note also that there is actually a bandwidth of system costs, which is well illustrated in the Solar Heat Worldwide report, and the reference systems here are typical systems within this bandwidth. key factors and outcomes of this comparison, we can see the specific solar yield is in Austria and France more than 30% higher in multifamily house in comparison to single family house, which is good in terms of energy payback time for the system. But probably is also due to a smaller solar fraction. Concerning the investments, there we see an interesting economy of scale, which ranges, depending on the country, from 14 to 36% of the specific investment, and it leads in the end to levelized cost of heat, of solar heat, which are lower than conventional heat in Austria, similar in Switzerland, and in Denmark, even in single-family house, the levelized cost of heat are lower for solar heat than conventional heat. In France and Germany, we see the cost of solar heat are about 10–15% higher than conventional heat. But I want to mention here that in the hypothesis for this calculation, the conventional heat is not supposed to increase. It's supposed to stay constant over the lifetime of the solar system, which is actually not guaranteed. And actually that solar heat is more predictable and stable over the lifetime of the installation. So now how to ensure that the costs, the low costs are actually met? It is important to share the experience from existing systems to avoid and learn from potential errors. And out of this experience, impose good practices in all steps of the project. So, some measures have already been discussed. I want here to mention the work of the Sokol initiative in France, which is gathering other 2,000 members, professionals and contractors, which aim is to set up the conditions for an efficient and sustainable use of solar thermal heat, solar thermal energy in multi-family houses. So about good practices in the design phase, it's good to use proven hydraulic concepts, which enables to avoid errors and also focus on simple, efficient, robust hydraulic concepts. Good sizing of components is, of course, important, and the standardized has been described in detail by Stefan, and can also help in multi-family houses. The implementation in the building, there is an easy, that if the building is well designed or the renovation concept is well thought, then easy access and installation on the roof can be secured, and the hydraulic system can be fastly implemented. The dynamic commissioning is also very interesting. It consists in checking that the solar system is actually delivering the expected yield in the first months of the real operation of the system, and it can help correct the regulation system, control system, or quickly. During the lifetime, it's also important to monitor the operation. It can be in combination with or not with production contract or production guarantee. But it's good to have even a simple measurement system to track the outcome of the output of the system and detect quickly any potential reduction in the output and perform the maintenance accordingly. So further cost reduction potential There are some interesting emerging approach. Well, I have talking about solar domestic systems, but solar domestic hot water systems. Combi systems can also be interestingly combined with activation of building thermal system, building thermal mass, where solar heat can be directed in the thermal mass of the building, the ground, the ceiling or the floor. And another interesting approach is to integrate solar heat on the return line of two pipes distribution network, which is distributing space heating and decentralized hot water preparation. In both cases, solar heat can be delivered at low temperature, which increases the efficiency. Combination of solar and heat pumps are also interesting, where collectors can be sourced for the heat pump or using hybrid PVT collectors, photovoltaic and thermal collectors. And about business models, I want to say that the solar, thermal, and renewables are sometimes already more cost-effective than conventional systems, but business models don't necessarily indicate that or make this visible, because the cost structure of renewable energy is different. So innovative business model can help make this cost advantage visible. Just to sum up, we have shown that the LCOH is already it's not yes, sorry, the key message is so there are in some cases attractive costs of solar heat thanks to the significant economy of scale in multifamily houses, which is sometimes lower than the conventional cost, and definitely more stable and predictable than fossil fuels, which is an incentive to choose this heat energy. And it's also important to share experience and impose good practices to guarantee low achievable costs. And emerging approaches include the thermal activation of the thermal mass of building in combi systems, as well as combination with heat pumps and innovative business models. With this, I want to thank you for the attention, and I hope we have can answer some questions.
Thank you, Francois, for this presentation, for this last one about practical examples. Well, we've now seen that there's quite a lot of approaches how to lower costs, and all of them are quite different. And the big question that is haunting us in this last year of Task 54 is how to bring them all together, actually. And our operating agent, Dr. Michael Köhl, from Fraunhofer ISE, has summed up the potential we have shown today and is trying to bring all of these aspects together in his wrap-up that is following now.
So, hello, ladies and gentlemen. I have to apologize that we needed much more time than we expected. I hope we have presented to you some of our findings in a way that you could follow, and there are some more, so feel free to keep in contact with us anyway. So I wanted to sum up a little bit, but yeah, here we made a questionnaire in addition to find out the costs of installation and of the systems, and you can see here the outcome of the system price, as you can have seen already sometimes before, around 800 euros per square meter. It seems to be a standard price, except in France and in Switzerland, where the systems are much more expensive. Weak point is, of course, the high installation costs, and I guess we have tried to show you in which way we will get to more easy installation and more straightforward sales policy. in total, this cost distribution looks like that. You need about 10% for planning, 38% for production, 12% for distribution, 16% for installation, 24% overall overhead costs in addition. And we have seen that our reference system has about 13.9 euro cent per kilowatt hours in cost. And these numbers are the relative percentage of cost reduction we could imagine. We have seen there is a potential in temperature limitation also for maintenance and operation, where we can get down in cost. There is also the possibility to get to a higher service lifetime, and these together and standardized components can yield in about 30% cost reduction roughly. So that's something which is a target which could be realized without big actions. Another point to get down in costs much more, as we have heard from François, is to go for multifamily houses. That means bigger areas, bigger systems, and respectively lower prices, or to go for a completely new concept like the polymer concept shown by Michaela, where we can finally already face a reduction of 50%. So that's my summary yet. We are continuing working and try to find out some additional ways. And now I'm handing back to Sandrine, because she has to manage answers or questions of the end.
Yes, thank you, Michael. So unfortunately, we've run out of time, but we might allow maybe one question just to start with. And we've just decided throughout this webinar that we will collect all of your questions and even more if you want to send them to us on our homepage. So we'll provide a Q&A document for download for you afterwards if you feel that your questions haven't been tackled within the last presentations. But there's been one question that popped up, and I quite like that. It's a question for Stefan, and maybe you can tell us a few words about this. There was someone who wanted to know that who would be the relevant institution to implement the standardization you have suggested on an international level, which would be the bodies to talk to, and what kind of potential do you see in having this actually work?
Well, actually, the intention is not to introduce a regulation or something like this, so everybody is forced to build or to do all the standardization steps. The idea is rather to give a proposal so that everybody who changes or develops a new collector can adapt to this standard. Yeah, so we are not looking for regulation. And if I may add something, which is the outcome of the project up to now, is that it's much more or the potential of the interfaces between the components hold much more potential than the components itself. So because this is what the installer has to deal with, to connect the different components to each other. And if there are standardized solutions, that will help a lot.
Okay, thank you for this very comprehensive answer, Stefan. Well, unfortunately, we don't have time to have more, but as I said before, feel free to keep in touch with us and really send us your questions and all your comments you might have. You see my address on our slide below. And we also would like to invite you to our next workshop in Sophia Antipolis. If everybody of you happens to be in southern France on the 26th of April, feel free to join us. Also, the information is available on our homepage. And with this, I'd like to thank our speakers. I'd like to thank every one of you for listening, and of course, also ISIS and the Solar Academy for hosting this event for us. And with this, I hand over to Joanna.
Thank you very much, Sandrine, and thank you for moderating this excellent webinar. I think it goes to show how much questions we got in, and that the audience was really interactive and listening and eager to learn more. So I really appreciate the Q&A that you're going to be posting on that website. That's fantastic. Thank you to our panelist speakers for sharing your knowledge and expertise with us today. And especially thank you to the Solar Academy for organising this webinar. As Sandrine explained at the beginning, they are held quarterly, so do be on the lookout for the next one. Will possibly be taking place in the summertime. To contact the panelist speakers for further information about what they have presented here, please see their own contact information in their presentations, which is available to download right now on the ISIS website. I included Johan's presentation again because his LCOE formula wasn't showing up in the first presentation, but it's now available in a second additional presentation on the website, so have a look. If you use social media, we encourage you to connect with us to continue the discussion and to stay in tune to what's happening with solar heating and cooling and renewables all around the world. Last but not least, thank you to our audience from all corners of the world for joining us today at whatever time it was for you. We look forward to welcoming you back to the next ISIS webinar. You may view the webinar recording in a couple of hours on the ISIS website, YouTube channel as well. If you have comments or feedback, we welcome you to share this with us so that we can continue to improve this service for you. Please complete the survey or send your feedback to public.relations@isis.org. Again, thank you so much to everybody. It was a fantastic event. I hope you enjoyed it as well. Wishing you all a great day or evening, whatever time it is in your part of the world. Bye-bye.